Okay, so we get this idea of an inner product. Okay, and what an inner product is like if I'm working in a vector space that's not Rn, how do I define something that works exactly the way the dot product does? So in order to do this, I want it to have 1, 2, 3, 4 characteristics. So I'm going to create an operator. I'm going to eat two vectors, u and v, and this is going to be my operator. It's going to return a real. Okay, but I want it to have 4 characteristics. 1, I want it to be commutative. So u times v is the same as v times u. Number 2, I want it to be distributed. U times v plus w has to be the same as u times v plus u times w. Okay. The third one, I want it to associate a scalar. So if I take c times u times v, it's just going to be cu times v. It only multiplies against one of the terms, not both. Okay? And I want something that's multiplied by itself to be positive or 0, non-negative. And the only way that something multiplied by itself can be 0 is if that thing is the 0 vector. Okay, if I've met these 4 criteria, I have an inner product. Okay, so like the dot product is an inner product. Okay, but we're going to give some examples here. Like if I'm in R2, so u and v are in R2, I can create a different inner product. I can say that u times v is like u1 v1 plus 2u2 v2. Okay, and you can check. This is actually going to make all 4 of these things true. It's a funky type of like a dot product where like I've scaled the first one as a 1 and scaled the second one as a 2, but it's going to work. All right, so we can play this game with like polynomials, right? So let's let p be a0 plus a1x1 out to an xn. Let's let q be a b0 plus b1x1 out to, or sorry, whoa, that's not right. Let's fix this. Thinking too fast. Want it to be not x1, I want it to be a1x plus a2x squared. There we go. Out to an x to the nth. And there we go. Q is going to be, these are polynomials. b0 plus b1x plus b2x squared plus bn out to x to the n. Okay, so I've got 2 polynomials. And we're going to define the inner product of p and q as like a0 times b0 plus a1 times b1 plus a2 times b2 out to an times bn, which, hey, that looks a lot like the dot product, but it's just using the coefficients of the polynomial. All right, but that will meet all 4 of these criteria, so it's going to work. All right, so let's get a couple more that are pretty commonly used. All right, so you could do one with matrices, right? So you could have a matrix A where you have A11, A12, A21, A22, a matrix B, which is B11, B12, B21, B22, and I can say that the inner product of matrix A with matrix B is A11, B11, plus A12, B12, plus A1 or A21, B21, plus A22, B22. And that's going to give me a real number that meets all 4 of these criteria. Okay, so one last one that's kind of commonly used, but it's a little tricky when you think about it, of it as like a dot product. We're going to enable a little bit of calculus here. We're going to let f and g are going to be continuous functions on the interval from a to b. And we're going to say that the inner product of f and g is actually going to be the integral from a to b of f of x times g of x dx. Now, if you stop and think about that long enough and hard enough, you're going to see that that's like a continuous kind of dot product over a function. But the reality of this is that this, if you kind of work it out, is going to meet all four of the above criteria. Now, once I meet these four criteria, I get a whole bunch of other things that work the same way that the dot product. All right, so we have a theorem. Okay, so my theorem says the following things are also true. If I have an inner product, then 0 inner product with any vector ends up being equal to that vector inner product with 0, which has to be 0. Okay, woohoo. All right, the second one is that not only do I get left-hand distribution, I also get right-hand distribution. So I can do this, which is going to be u w plus v w. So I can distribute on both sides. Another quick property that I get is that if I have the scalar on the second term, that's the same as the scalar times the whole. So the scalar can go on either one of the components of the inner product, but it cannot go on both. Okay, so the other thing that's going on here is that I can induce what is called a norm and a distance and an angle measure from this inner product. Okay, so norm, distance, and angle measure. Okay, just like I could induce these from a dot product, I can also induce them from an inner product. Okay, so number one, the 2 norm of some vector is the square root of the dot product or the inner product with itself. Okay, so we call this the 2 norm because it's using a square root. Okay, so this is the 2 norm. So that's like a measure, right? That's a metric. I can find the distance between two vectors using this induced idea, and that's just taking the norm of the difference of the two vectors. However, subtraction is defined in the vector space. So that's a distance. And then I can induce an angle because I have my law of cosines. The cosine of theta is going to be the inner product of u and v over the norm of u over the norm of v. And if I can say that this is angle measure, then if the inner product happens to equal 0, then we have this idea that u is orthogonal to v. So it's a little weird to say that like two polynomials or two matrices or two functions can be orthogonal, but in fact we can, because we have a metric by which to establish when they are orthogonal. So let's look at some of this. Okay, so let's let p be 1 minus 2x squared. Let's let q be 4 minus 2x plus x squared, and these are going to be in P2. Right, so their inner product is going to be 1 times 4 plus 0 times negative 2 plus negative 2 times 1, which is 4 plus 0 minus 2, which means their inner product is 2. Ah, so that worked. Okay, so let's try to take like the norm of q. Like what's the size of this polynomial, right? So the norm of q says I take the square root of, well, that's going to be 4 squared plus negative 2 squared plus 1 squared, right? So this is 16 plus 4 plus 1. So this is the square root of 21. That's the size of q. And I have no idea what that means, but I was able to induce some sort of norm and a size. And if I want to know the distance between these two polynomials under this inner product, well, let's see. In the first term, I'm going to take 1 minus 4 squared. In the second term, I'm going to take 0 plus 2 squared in the third term. I'm going to take negative 2 minus 1 squared. So let's see, this gives me 9, 4, 9. So that's 13 plus 9 is 22. So the distance between these two polynomials is the square root of 22. Now, again, what does that distance mean in reality? I have no idea, but I do know how to take a distance according to this inner product. So let's make this even more weird. Let's say that f is the continuous function x, and g is the continuous function x squared, and that these things are continuous functions on the interval 0 to 1. Okay, so in this vector space, the norm of f, the 2 norm of f, is going to be the integral from 0 to 1 of x dx, right? So, it's going to be, sorry, let's back that up. It's going to be the f times f inner product dx, which is actually the integral from 0 to 1 of x squared dx, right? So that's like 1/3 x cubed from 0 to 1, which is just 1/3. So literally the size of the function f of x on the interval from 0 to 1 under this inner product is 1/3. Now again, no idea what that means, but who knows? All right, so let's try to figure out like what would be the distance from f to g. So let's get a little bit of space here because this might take us a little bit of work. Let's delete that. Okay. So here's how we play this game. I'm going to actually find the distance squared. And so here's the distance from f to g squared. It's going to make my computations a little easier. Okay, so this is the integral from 0 to 1 of f to g sorry, that's not it. That's not distance. Of the norm, right, of f minus g, right, squared dx. Okay, so this is 0 to 1 f minus g dx, which, okay, so this is f minus g is x minus x squared, and then we're going to square that, right, dx. So this is the integral from 0 to 1 of x minus 2x cubed plus x to the 4th dx. Okay, so take the integral, x squared, right, because we're squaring here. There we go. 1/3 x cubed minus 1/2 x to the 4th plus 1/5 x to the 5th from 0 to 1. So that's 1/3 minus 1/2 plus 1/5, which I think works out to be 1/30th. So if this is the distance squared, this would imply that the distance from f to g would be the square root of 1/30. Again, no logical interpretation there of what that might mean, but given the induced metric under the inner product, that gives me a well-defined distance. Okay, not necessarily a well-applicable one, but one that's well-defined. So with this idea of a norm, a distance, and an angle, I get a whole bunch of truths. The norm is always non-negative. 2. The norm of a vector is only going to be 0 if the vector is the 0 vector. If I take the norm of a scalar times the vector, that's equal to the absolute value of the scalar times the norm of the vector. So when it comes out as an absolute value. The distance from u to v is always non-negative. The distance from u to v will only equal 0 if and only if u is the same as v. And 6, it would make sense that the distance from u to v should be the same as the distance from v to u. Now, ironically, we also get Cauchy-Schwarz here. The absolute value of the inner product of u and v is less than or equal to the norm of u times the norm of v. We get the triangle inequality is that the norm of u plus v has to be less than or equal to the norm of u plus the norm of v. And we also get a Pythagorean theorem that the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared if and only if u is orthogonal to v. Okay, so Cauchy-Schwarz, the triangle inequality, and the Pythagorean theorem all still hold from the last video. Okay, so there you go. This is your intro to inner products, which is a lot like dot products, but on the general vector spaces.